Hello everyone, welcome back. Today we'll solve problem 95 in DeepML, which is called calculate the Phi coefficient. So in this problem, we're given two lists, X and Y. Both of them have elements that are either 0 or 1. And what we're going to do is we're going to calculate the Phi coefficient amongst them. Now, if you are not familiar with this coefficient or if you need a refresher, I'm going to first dive into what the coefficient is, why is it important, and when do we use it. And afterwards, I'm going to code my solution, which is going to be somewhat different from the official solution. But I'm doing it that way because I think it's going to be more clear, especially for those of you who have never seen this before. So without any further ado, let's dive in. So the Phi coefficient, which you can also find referred to in the literature as MCC or Matthews correlation coefficient, is, as the name says, a coefficient that tracks the correlation between two binary variables. And I'm going to explain a little bit more about that in the moment, but it's usually used in cases where you have opposing classes in a binary classification problem. So what I mean by that is my typical example. Let's say you're building a classifier that gets an image and tells you if it's an image of a cat or not. Well, in this case, this is a perfect example for the kind of problem that we're trying to solve with this coefficient, because the photo can either be a photo of a cat or not. There's no middle ground. There's no half cat. We're not talking about Schrodinger's cat here. So with that in mind, what this coefficient does, or the reason why we care about it, is because it helps us track the class imbalances. And I'm going to talk about that a little bit with a motivating example. So the typical example that motivates a class imbalance in binary classification is when you build a spam classifier. So let's say you were building something that tracks emails and tells you if it's spam or not. So luckily, well, depending on which websites you frequent, but luckily we can say that spam is relatively smaller compared to the other types of email you should be getting on a day-to-day basis. So let's say, for example, that 1% of the emails that you get are spam, and the other 99%, that's supposed to be a 1%. I'm very proud of my handwriting, but this is supposed to be 1%. So 1% of what you get spam, 99% is not spam. We can see that there's two classes here. So usually the type of classification that, or the type of metric that comes to people's mind is accuracy, which means, oh, we're just going to build a classifier, and however many emails it classified as spam correctly, or those that classified as not spam correctly, then that's the metric that we're going to guide ourselves from. But if you look at this, well, one thing you could do is you could say, well, everything is not spam, or in the positive, nothing is spam. So if you did that, then your classifier would have a 99% accuracy. So your classifier is basically telling you, don't worry, man, nothing is spam. And it's, if you work with that metric, it works 99%. But is that really something that we care about? Is that something useful? No, it's not, because, the class are imbalances. So accuracy doesn't work. So very smart people usually come up with the confusion matrix, which you may have been familiar with. And if not, well, there's a great problem that I made myself on DeepML that you can use. So what the confusion matrix does, for those of you who are not that familiar with it, is it tells you how many observations were actually labeled in the class that you wanted. So let's say 1 stands for positive, 0 stands for negative. So the true positives are those that were actually positive and were labeled as positive. The false positives are those that were actually negative or were labeled as positive, so on and so on. So when you're dealing with this type of situation, or when either the false positives or false negatives matter more than the other, then you start to use other metrics and you work usually with this type of confusion matrix. But here comes the problem with the confusion matrix. Or maybe it's not a problem, but it could be a limitation. So the nice thing about metrics like accuracy, recall, that kind of stuff, is that it's just one number. It's very useful. You just say a number, you look at the number, and if the number is above a certain threshold, then you're golden. That's exactly what you want. But with a confusion matrix, you don't get that because you're going to have a matrix and you have to look at these numbers. And if there's 1 million true positives, well, what does that say, right? Maybe I have 100 million observations, so maybe that's not too good. So then you can normalize it. Yeah, and that's going to give you some idea. But if you just look for examples of the true positives in isolation, you're not going to be able to take much out of the whole matrix. All of that is to say, when you're looking at a confusion matrix, you have to look at multiple numbers at the same time. And there may be situations where that's not useful. So here comes something that people have said is perhaps the best approximation as a single number, which is our Phi coefficient, or the Matthews correlation coefficient, if you want to give credit to the alleged author. I'm saying that because apparently Pearson discovered it first. So what this thing says is it tells you the correlation between how many observations were labeled as positive and were actually positive, and similarly with the negatives. And it summarizes all of this into one neat number that can serve as a guideline. Again, if you want the full story, you should look at the confusion matrix. But if you want to have a quick and fast dirty rule, you're going to work with this number. And this has a neat formula. So it's a fraction. What we're going to calculate is true positives times true negatives minus false positives times false negatives. And we're going to divide all of that by the square root of true positives plus false positives, and that multiplied by true positives plus false negatives. And you can see where I'm going with this. Then we're going to multiply true negatives plus false positives. And hopefully I don't run out of space, but we have to include true negatives plus false negatives. And so you have this huge expression. And what this huge expression does is it tells you how related the number of observations are. And it's usually used in cases where you have a class imbalance. Now, there's no actual factual rule where you say, oh, if your Phi is 0.77, then this is fantastic. And if it's 0.76, it's not fantastic. But there are certain guidelines that you can use. So remember, this thing is measuring correlation. It's not telling you much else about the problem. But if Phi were to be 0, then what this is saying is that there's no relationship. So there's pretty much no correlation between those observations that were labeled as positive and those that were labeled as negative. If your Phi were to be 1, on the other hand, what this means is that there is a perfect positive relationship. So these things, both classes are very related to each other. They're perfectly correlated. And similarly, we can have the same with a -1. So you can call perfect negative, I think that's the name, relationship. So now that we understand what this thing is and why it matters, let us first write the skeleton of our code. And then I'm going to talk a little bit about how it is that we're going to do all of the parts of it. So what I mean by the skeleton of the code is that I usually like to start with the certain comments that tell you what the code is going to do, and then it's easier to order your ideas and be able to code it up. So first of all, we're going to do something that it's optional, but it helps me a lot to make my code more neat, which is to define a variable for the length. So this is just going to be, and I'm going to type it out immediately so you can see what I mean, n equals length of x. So that's just going to tell us how many observations there are. So now what we're going to do is we're going to generate variables for each of the 4 cases. So what I mean by that is we're going to generate a variable for true positive, true negative, false positive, false negative. And now after that, the Phi coefficient, remember, is a fraction. So what I always like to do with fractions is calculate numerator and denominator separately. This is not necessary, but I think that it makes your code more neat and it makes it easier to follow what it is that you're doing. And after that, we're going to combine numerator and denominator. So that's that, and then we end up making the return. So we're going to do something like val, and I'm just using the placeholder name that comes here, and I'm just going to define in different lines numerator and denominator. Now, the last thing I'm going to do before I start coding is I'm going to import math, the math library, and that's because we're going to use the square root, remember, in the formula. So math is just a neat way of doing it. Now, what do we call the through positives? Well, it's those things where both variables, both x and y, predicted 1. That's the value that's given. So the way I'm going to generate all of this, and remember, there's just simple combinations, right? The true negatives are going to be when both of them say 0. The false positives are going to be when x tells you 1, but y is 0, and so on. It depends on how you want to label stuff. It doesn't really matter. But for the purposes of this question, what I'm going to do is I'm going to generate this in the following way. So I'm first going to generate a list. And this list is going to be a binary list. Binary list that tells you 1 when this is observation 1 if observation I is a true positive, and 0 if not. And Python, I'm going to tell you a little bit about why I'm doing it that way, because there's different ways of doing it. So the value of these things is going to be 1 if x of I is going to be observation I equals y of I, which equals 1. So this is a neat way in Python that you can say that both of them equal 1. Now, some people don't like to write it this way. Some people argue that you should write xi equals 1 and iy equals 1. This is going to run. It just depends on how neat you want to be. And if not, then this is going to equal 0 for I in range n. So this is a list comprehension. We're just generating a list pretty much in place by doing this type of procedure. Now, we don't care about the list itself. We don't care about which particular observations were true positives or not. What we care is about how many of them. And we can do that by just summing. And this is why I typed this code this way. So what this is saying is that you're going to generate a list that's going to be equal to 1 whenever you have a true positive, 0 when not. And then you're just going to sum all of those. And if you sum all of those, then it makes sense that you're going to get the number of true positives. So that's the procedure that we're going to follow. And I said at the start of the video that's different from the official solution. In the official solution, they go using a for loop through all of the observations, which is fine. It makes sense. I just feel that this is a new way of doing it, and it teaches you something new, if not. So now for the true negatives, well, kind of the same idea, but instead of having it equal 0, both of them equal 0, they're both of them going to equal, instead of both of them equaling 1, they're both going to equal 0. False positive, again, this depends on how you label your data, but I'm going to say that x is going to be our predicted and y is going to be our actual. So wait, no, it should be the other way around. Excuse me. So x is our predicted, y is our actual. And what I'm saying here is that we're predicting 1 when in reality it's 0. So that's a false positive. And then notice how I had to change it into 2 conditional statements. And for false negatives, we're going to have kind of the same thing. Now, with all of that, we have all of the parts that we need to write the numerator and denominator of this fraction. So the formula was true positives times true negatives minus false positives times false negatives. And then we're going to divide that by the square root. Well, maybe, yeah, this is going to be even cleaner. I'm going to take the square root apart just so you can see how you can modularize this. So we're going to have true positives times plus false negatives, false positives times true positives times false negatives. And then we're going to have to multiply these two. I'm going to be kind of lazy, so I'm just going to copy this and change true positives for true negatives. And afterwards, we're going to take the square root of that, which is the last step for the denominator. Then we're going to divide these two things, and then gives us our final result, which here is called val, but that's a Phi coefficient. And so we're going to run this thing, and hopefully we don't have any problems with it. And there we go. We pass all of the test cases. So as you can see, this problem can be a bit daunting if you haven't seen this coefficient before, but now that we understand it, and now that we see that it comes from just a simple formula, we can type it up. Again, you can do this multiple different ways. I feel that list comprehensions are very intuitive, very Pythonic, which means that you're taking advantage of the way that Python can handle stuff. And it's also a neat way to practice because it's something that can help you a lot. So thank you so much for watching. Let me know if you have any doubts, questions, suggestions, and I hope to see you in the next video.